Hey everyone, welcome to Lecture 11. Today we're going to kind of pick up where we left off with determining what kind of chemical equations we're working with. And then we're going to add some math in towards the end. So if you want to grab a calculator to be able to do some calculations with me, and then also make sure you have your periodic chart. Pause the video now if you don't have those items and go get them so that you can follow along. So we were talking about all different types of reactions, and you had a quiz on the types of reactions, and we went through combination reactions, decomposition reactions, we went through double displacement and single replacement reactions, and kind of left up on neutralization reactions. We're just going to reiterate the neutralization reactions and what they are, and then work with some of them. So again, when we talk about a neutralization reaction, we are talking about a reaction between an acid and a base. And so those are going to be the two chemicals that we'll put in. So here you see an acid, and we know it's an acid. Let me change it to red so you can see it. We know it's an acid because it starts with a hydrogen, okay? And then our base is right here, and we know it's a base because it has that OH. And OHs are generally indications for bases. Okay, so when we mix this acid and base together, what we end up with is some sort of salt, which we get this from right here, okay? And this from right here. So they've kind of done a double displacement reaction. And the B and the X have switched partners. This ends up being a salt, and then we also end up with water, or H2O. So what's actually happening with the neutralization reaction is that we are taking these acids and bases and we are causing them to be less reactive, or bringing them down to a normal pH. So they're not considered an acid pH or a base pH, but they're just this salt, okay? So again, here we're dealing with an acid, you see the hydrogen there, and here is our base. They're coming together to form, and then this one, this K and this SO4 become new partners, KSO4. Okay, and then the other product that we get out is water. So a neutralization reaction, you should be able to pick one out just by looking if it's creating a salt and water. Okay, also make sure you're putting in an acid and a base. Okay, so again, that was just reiterating something we had said in the last lecture. We also talked about precipitation reactions, and most of the time these are double displacement reactions where we have to look at what's not soluble or what precipitates into the water. Okay, so we worked with several equations and just to determine what was soluble and what was non-soluble, but I told you we were going to come back so we could figure out what compounds or what chemicals in this reaction were actually doing all the work, because some of them were just watching. Okay, so we're going to work with this one, and most of the time we don't really care about what we're putting in, we just look to see if what we're getting out is soluble or not. So if you go back to your solubility rules chart, you'll find that both of these can be found on there in either the insoluble or soluble. Go ahead and try and figure it out on your own right now. Give me 2 minutes. Okay, might not have been 2 minutes, might have been a little less, but. So if you were looking at that equation and the solubility rules, you probably found out that PBI is not soluble. So it is going to form a precipitate or something other than the two solutions that are being brought together. Okay, and hence the color change. So we've got two clear solutions, and PBI forms this color change. Okay, so that is a precipitate. The other one we find out is soluble in water, so it's not going to show up at all, that NaNO3. All right, so now what do we do with this information? Once we know what our precipitate is, then we can do what we call a molecular equation. And again, we've discussed this once before, but let's break it down, okay? So all of this right here that's written out is our molecular equation. That PbNO3 2 aqueous plus 2 NaI aqueous yields PbI2 plus NaNO3. Okay, that is a molecular equation. Once we know this precipitate though, we can break this equation into what we call an ion equation. Okay, and we didn't discuss how to do this in the last lecture, but I want to talk about it a little more in depth now. Okay, so we look at each compound. So let's start, and I'll use different colors. Let's start right here. We've got Pb, and we have NO3. Okay, we know those are going to come apart. The thing that we need to figure out is what their charges are. Okay, sometimes you can look up charges, right? We learned how to look up charges, but sometimes you need to look at the compounds that are involved. And remember when we did that cross, where we bring a charge from up here and bring it down, and bring a charge from up here and bring it down. And so we'll be doing the reverse of that. We're going to be bringing the charges that are down up to figure out what their charges are. So if we look at Pb, Pb is a metal, so it comes first. So we know it's going to have a positive charge. And if we look right up here, I'll put it in green, there's a 2 there that we know we're going to bring up right here. So we know it is Pb2+. Okay. Now, to balance out this Pb2+, we know that this NO3 has to balance out that 2+. Okay. We also know there's 2 of them. So we can then determine that this is a negative, because if we have 2 negatives, that will cancel out a 2 positive, and that will be a neutral reaction, or a neutral compound. Okay, let's do the same for this one. We have Na and I. Na is an easy one because Na always forms a plus charge, which means that this I is also going to be a negative charge. Okay, with our precipitate, we're not going to break that up. We're going to leave that the way it is because it forms something completely different. So we can't break it up into ions. It's not separating. It's just staying put. So we're just going to bring that straight down like that. Okay, and then we have this last step. We have NaNO3. We're going to leave that NO3 together. And we know Na is always going to be positive. So we brought that positive 1 up there. And therefore, this Na has a 1 here that we're going to bring up here, but we know it's going to be negative. So Na, NO3, this one's positive, this one's negative. They cancel out. Okay, so breaking it down into the individual ions that are involved, we get something that looks like an ionic equation. Okay, so that's what that equation will be called, is an ionic equation, showing all of the individual ions that were in that equation. Now here's where the fun part comes in. Once we have our ionic equation, we can actually utilize this ion equation to cancel out like compounds on each side of the equation. So we'll cancel out something on one side of the equation with the identical item on the other side of the equation. So if we look, we have a 2NO3 here, negative, and on the opposite side of the equation, or on the other side of the arrow, we have a 2NO3 here. So we can cross them out. Okay, same with this. Na2, or 2Na plus, we can cancel out with a 2Na plus on the opposite side. Now, nothing else is identical, so we can't cross anything else out. So we're going to bring all of those down. Okay, so here I brought my Pb down, I brought my I down, and I brought my and change the entire equation. And doing this gives me my net ionic equation. This equation shows all of the elements or compounds that are actually doing work in this equation. Okay, so net ionic equation is the equation that does all the work. So even though we have different things like NO2, Na, NO2, none of those are doing anything, so we've crossed them out. Net ionic equations are important, and you should be able to find them for any reaction that we're dealing with. Okay. That being said, all the ones we cross out are what we call spectator ions. They're there, but they're just watching things take place. They're not actually participating. Okay, so they're called spectator ions. You should be able to identify in equations spectator ions, and you should also be able to identify net ionic equations. And some of these are on your homework for this week. Okay, and again, we talked about this picture. We just didn't talk about the molecular equations in depth. So we talked about this picture a little bit, and so you can see that if we put all these compounds in together, right, there's Pb, there's potassium, there's iodine, there's my NO3. When we put them all together, we end up starting to see that the potassium really isn't doing anything, my NO3 isn't doing anything, but we see this Pb and this I starting to clump together kind of in this group down here. And that's what's forming that yellow color, that precipitate. Okay, so keep these on the forefront, practice them on your homework, and you can definitely go online and find a lot of other examples and practice problems as well. And again, for all of these, I use that solubility chart, which tells us whether or not things are going to dissociate and disappear in water, or whether they're going to start to clump up and form something different. Okay, be able to read these and have these handy for your exam. Some other examples, like I said, that we showed on that first lecture. So let's practice, okay? I'm going to give you some rules and then we'll go ahead and do one. Okay, so the first thing that we need to do is, with our equation, we need to make sure it's balanced. Most of the time, I'll give you a balanced equation, but always check that. Okay, then you need to write the ionic equation showing all of the electrolytes and how they dissociate into both their positive and negative charges. Okay, that's after you've got a balanced equation, then we work on writing our ionic equation. Then cancel out all of your spectator ions, which were located on both sides of the equation. So we cancel one side with what's on another. Don't cancel anything that doesn't match. Okay? That's very important. If the charges don't match, if the numbers don't match, don't cancel them. You'll get in trouble, okay, with your answers. And then the last thing that you need to do is check that all your charges and numbers on your atoms are balanced in the net ionic equation. And form that final piece, that ionic equation. Okay, so let's work on this. Okay, we're going to write the net ionic equation for the reaction of silver nitrate with sodium chloride. Now I'll give you the initial equation. Here is silver nitrate, and it's been mixed with sodium chloride. Okay, and it is yielding a silver chloride solution and a sodium nitrate solution. Okay, so first thing we're going to do is make sure it's balanced. And I'll tell you right now, it is balanced, so you don't need to worry about that. Okay, let's look at these then and figure out which one is going to precipitate and which one is going to dissolve in the water or be soluble in water. Okay. So looking at your solubility rules, if you go through and try and find anything that contains that Cl, maybe, let's look for Cl first. And we go down our solubility side, and we find that halides, which include Cl, Br, and I, are all going to be soluble compounds, with the exception if they're paired with silver, mercury, or lead. So we know right now this one is insoluble because it is chloride paired with silver. Okay. If we look for that NaNO3, we're going to go down the chart and find that all of my nitrates are going to be soluble, and there are no exceptions. So that one is soluble. So this one we're not going to worry about leaving intact. We are going to break it up. This one we have to leave. Okay, don't mess with it. So let's break everything down now into ions, working with charges. Okay. Here, if we do that, I'm going to start here, and we see that we have NO3. There's a 1 back here. Remember, the first number is always positive, or first compound element, excuse me, and the second one is negative. So here, Ag has a plus, NO has a negative. Okay, we're going to do the same here. Na has a +1, Cl has a -1. This one we're leaving intact. It's our insoluble compound, so leave it intact. Okay, and then the last one, again, leave this together because it's showing up the same on both sides of the equation. My Na +1, my No -1. Okay, there is my ionic equation. Now we go through and cross things out. Okay, so I see an NO3 negative on one side and an NO3 negative on the other side. See an Na on one side plus and an Na plus on the other side. And what I'm left with then are things that can't cancel out, which is Ag plus and Cl negative, and yielding, again, my precipitate because it's not going away. And if I look at this, I see that I have one AgL right here, I have one Cl there, and I have one Ag and one Cl there. So we match, the equation balances. All of these guys would be considered my net ionic equation. That being said, I have some spectator ions that we canceled out. So NO3 negative and Na plus would be spectator ions. Okay. So let's just talk about acids and bases for a minute, because the next thing that we're going to introduce are really acid and base equations. And so when I'm talking about properties of acids, they all kind of share similar properties. So the first thing you should think is that most acids have a very sour taste. Okay, we eat things like citric acid in fruits, which kind of have that sour or puckering taste. Vinegar, it's because it's made up of acetic acid, and so it causes us to pucker. Acids are very easy to distinguish because of either their smell, which kind of causes your nose to burn or pucker, or because of their flavor. That being said, never taste anything just to figure out whether or not it's an acid. One of the other things about acids are, because the pH is different than normal water, we can actually use plant dye and determine whether or not it's an acid and a base. So we use different pH papers that are dyed with plant product. And acids will either cause that paper to turn blue or cause it to turn red, depending on what kind of paper we're using. So we can cause color changes just by using an acid and plant dyes. Acids also are going to react with metals. And most of the time when they react with a metal, we are going to see the production of hydrogen gas, so some sort of bubbling or fizzing or carbonation occur. Okay, so here's an example. We've got hydrochloric acid right here mixing with magnesium, which is a metal. We get a magnesium chloride and the release of a gas or some bubbles. Okay. If we put it with carbonates. And so when I say that, I'm talking about things like CO3. That would be considered a carbonate, or a bicarbonate like Na2CO3, CaCO3, NaHCO3. Any of those would be considered carbonates and bicarbonates. Okay, anytime we pair it with something, an acid, here's our acid, and we know it's an acid for two reasons. It's aqueous and it starts with that hydrogen. Okay, when we put those with those carbonates, then we always get a metal. In the first one, we get that CO2 gas, and we get water. Okay, so we should always see carbon dioxide gas being produced from it. The other thing that we'll find is that all aqueous acid solutions conduct electricity. So most of my acids, we should be able to put a current through. Bases are a little different. So bases, when we think of bases, we think of things like bleach, or things like a lot of the things we clean our house with, honestly. Most of these have a bitter taste. If we get them on our fingers, they feel very slippery. And so soaps are a good example of bases. We use lye, which is a base. Bases can also cause color change in plant dyes because the pH is different. And with our aqueous base solutions, we'll also be able to conduct electricity. So with bases, they're willing to dissociate, acids are willing to dissociate, and some of our most common types of bases would be our OHs. So anytime you see OH, you should think base, although some of our bases look like this, and those would be left up for me to really tell you which one was an acid or a base if you're not familiar with recognizing them. There is a figure, table 4.3 in your textbook, that lists common acids and common bases are also listed on another figure, which I don't have right in front of me, but I encourage you to look at those so you can kind of start to familiarize yourself with what acids and bases look like. Okay. Trying to find the figure, but I don't see it. Okay. Now that being said, we have different understandings of what acids and bases are. And so we are going to look at two basic definitions for acids and bases. And I want you to be able to distinguish between the two on your exam. Okay, so the first one, or the first definitions of acids and bases that we're going to talk about are what we call Arrhenius acids and bases. And this was basically given, it's the more common, I think, that we use in chemistry, probably. Maybe not, it is for us. But basically, it tells us how to determine what an acid and a base are. Okay, so according to Arrhenius, acids are substances that produce hydrogen in water. So if we are dealing with the equation hydrochloric acid plus water yields H3O plus Cl, we would be dealing with an Arrhenian acid because we are producing hydrogen right here with our water. Okay, we have overproduction of hydrogen. So bases then, sorry, I was trying to find that figure. I don't know why I can't find it. Bases are substances, according to Arrhenius, are substances that produce OHs in water. And so here you can see we start off with water and NH3, and what we end up producing down here is an OH. Okay, so the difference between Arrhenian bases is that we see an OH, and Arrhenius acids, we see an H. Okay. So that is the definition based on Arrhenius. Now we're going to throw in another guy. There's an example of a hydronium ion, which is also an acid. Okay. We're going to throw in definitions by another guy, Bronsted. And so Bronsted kind of expands the definition or broadens the definition of what an acid and base are. And he says that an acid is anything that can donate a proton, okay? And normally our proton is hydrogen. Okay, so an acid is going to donate a proton. A base is going to take on, so this is going to donate, and a base is going to accept a hydrogen or a proton. So for example, if we're dealing with this equation here, we have NH3 plus H2O yields NH4 plus and OH. Okay, now if we were to look at those, hopefully what we would find is that we have some pairs, okay? And the pairs are always going to be based with like pairs, okay? So here we have a base, and it is going to be paired over here with this. And we know that because they look almost identical. The only thing changing is the number of hydrogens. Then we have another pair that is right here, and is pairing right here. The only difference between these two are the amount of hydrogens. So these are pairs. So we always can form pairs when we're looking for Bronsted acids and bases. And then the one thing that we want to figure out is which one has more hydrogen and which one has less hydrogen. Okay, so if we look here, NH3 has less hydrogen than NH4. So a Bronsted acid has more hydrogen than a Bronsted base, which has less hydrogen. Okay, if we look at this other pair, we see that this one has more hydrogen and this one has less hydrogen. Here's my acid, here is my base. Okay, more hydrogen, less hydrogen. Let's try another one. Okay, to be able to donate this proton, we obviously have to have one or an extra one. And so our acids always need to contain more protons or more of those H's. Now, we can also have a couple of other vocab words that I'm going to throw at you. Okay, and I'll pop all of this up first and then talk about it. So the first one we're going to talk about is monoprotic acid. So mono, anytime you think mono, I want you to think one. Okay, mono, think one. So with a monoprotic acid, this is an acid that dissociates once. So in terms of HCl, I have one hydrogen. And when it dissociates, it's going to dissociate into a hydrogen and a chloride ion. Okay, it can only dissociate once, and that's it. Here, HNO3, again, when it dissociates into that H and that NO3, it dissociates once. Because these dissociate completely, we call them strong electrolytes. Okay, not all compounds are like that, but they can still be considered monoproduct. So in the case of this one right here, we're going to lose this hydrogen just once. And when we do that, we end up with hydrogen and then the rest of this compound. This is probably acetic acid, which we know is a weak electrolyte. Okay, it doesn't break down completely. There's still carbons and hydrogens and oxygen hooked up, but we lost the hydrogen, and only one. Okay? Monoproduct acid, loss of one hydrogen. Okay? Diproduct acids are going to be acids that lose hydrogens a couple of times. Okay, so if we're working with this compound here, H2SO4, and we break it down one time and lose a hydrogen, we end up with HSO4. Okay, that's the first time it breaks down. Then we're going to take this down here and break it down again, and we end up with a hydrogen and that SO4. Okay, so this one can be broken down twice. This would be considered a strong electrolyte. This one, a weak electrolyte. Okay, triproduct. So diamond 2, tri means 3. This one we're going to break down 3 times. Okay, so if you see our starting product has 3 hydrogens. We break it down once and we end up with 2 hydrogens in that compound. We use that as our new starter compound for right there, H2PO4 negative, and we yield an extra loss of hydrogen and HPO4, 2 negative, right here, HPO4, 2 negative breaks down into H and PO4. Okay, triproduct acids, we have to yield 3 different hydrogen ions. Then most of our triproduct acids in this case are going to be weak acids. And so weak acids, you see this, if you look at the trends, all of our weak acids have these double arrows, meaning they're not really sure if they want to complete that reaction or if they want to go backwards. So all of our weak electrolytes have double arrows. All of our strong electrolytes, they dissociate and they're done. They don't want to possibly change their mind and reconstruct that compound. Again, this is the table in your book that have strong and weak acids on them. You might want to know them because I might ask you about some of the dissociations between these acids. Okay, let's look at the following species of Bronsted acids and bases and tell me what they are. Okay, so HI, Bronsted acid or base, CH3COO, Bronsted acid or base, and H2PO4. Talk about those. Okay, so here's your first equation. Okay, so correct answer for number 1, hopefully you put Bronsted acid if you didn't see me change it earlier. Now, the reason this is a Bronsted acid is because if we pick its partner, right, acids always have more. And so if we look at the partner here, one of these has more and one of them has less. So HI would be considered the acid because it has more hydrogen. And and that I. Okay, what about this one? Try this one on your own. Hopefully you said it's a base because we are looking at this compound, which is this one right here. This one has less than its partner, which is right there, and that one has more. Okay, so this then would be a base. Last one. Look at this equation. Hopefully you said, well, this pairs with this. Okay, and you said that that H2PO4 was an acid because it has more hydrogen than the HPO4 2 negative. Okay, let's try this one. Hopefully here you said that it is a base because this has H2, this has H3, those are the pairs, so this one would be your acid, this one would be your base. All right, last thing that we're going to talk about today. This one takes practice, but you'll get there. We'll do a lot of practice too. And it's what we call oxidation reduction reactions. So these are reactions where we really focus on the electron transfer between compounds. Okay, and these are probably the ones that you should expect to see most often on your exam, because I do like these a lot. Oxidation reduction reactions are probably the most common reactions that you're going to see within any of your inorganic chemistry classes, and some of the most important reactions that we're going to see when it comes to the oxidation of metals or any other thing basically in water. So we're going to look at all of these pretty in depth. Okay. So when we talk about oxidation reduction reactions, we really need to look at the two words that are used in the title, which are oxidation and reduction. And for most of us, if we can remember the acronym oil rig, you should be able to remember everything you need to know about the oxidation reduction reaction. So oxidation, what's taking place always is that when we have an oxidation product, then we are losing electrons. So oxidation is losing electrons. Reduction then is the opposite. So reduction is gaining electrons. And so if you can remember oil rig, you'll understand what's happening in the equations. So if we look here, we know this is the portion of oxidation because Mg right here is going to go through the process of losing 4 electrons. And when it loses electrons, then we gain a charge. Okay. Here, with reduction, and we'll work through these will make sense more in the next slide. Our oxygen is actually gaining the electron, so the positive side is over here. We're gaining electron, and again, our charge is going to change. But because we're gaining electrons, we become more negative. Bringing on negative charges makes us more negative. So reduction is gaining electrons, becoming more negative. Oxidation is losing electrons or becoming more positive. And all of these can be taking place in the same reaction. So just like we've partnered things in the last reaction, we are going to partner things in this reaction. And really look at how things are changing. So if we look at Mg from here to here, and then we look at oxygen from here to here, we want to know how it's changing. And most of the time, it's with these charges up on top. Okay. Again, remember, if nothing is listed, then we just assume it's a +1. Okay, so with this one, then we have Mg +1 going to an Mg +2, and we have O +1 going to O2 negative. So we need to figure out what is happening within this reaction. We're not going to really worry about our electrons because the elements themselves tell us exactly what's happening. And again, like I said, we're just going to worry about the things that are left over. Okay, so I'm going to just briefly touch on this image because this is a good example of an oxidation reduction reaction where we can see both compounds at work. Okay, so we can see here, if we look at this first one, we are using zinc in some sort of copper solution. That's why it's kind of a bluish solution. So we've got a silver bar of zinc right here that's in this copper solution. And what's happening is copper is coming in and breaking away these pieces of zinc that are going and meeting up with part of the solution. And so you can see the portion of the zinc that's actually in the copper is starting to turn this blackish color, and down here you can even see some of the soot that's falling off of that zinc. Okay. Dissociation, we've got electrons being changed or converted from one element or compound to another. Here's another example. One of my favorites because it can make some really pretty structures. This is copper wire that's been put into a silver solution. And we know with copper wire that silver likes to come in and take pieces of it away. And so we end up breaking down most of the copper wire, but what ends up forming is this beautiful silver structure, or these little tiny crystals that you can kind of see up in this image. You know, right up here, you can see some of those beautiful structures forming. And that's just a concentration of solid silver. So when we look at these, again, if we go from Zn over here to Zn over here, and we look at the charges on both of them, then we'll find that this Zn goes from a charge of 1 or neutral to this Zn, which is going to go to a +2 charge. Okay? If it's oxidized, then it is losing electrons, right? Zn is oxidized, so it's losing electrons. If you lose electrons, you become more positive. Okay, down here, we're going from Cu2 plus to Cu, so this is becoming now more neutral. And so we see that we are reducing or gaining electrons, becoming more negative. And indeed we have. We've gone from a 2 plus closer to 0 or closer to negative, so we became more negative. Okay, now here's the confusing part. Don't get these terms mixed up, and I hate chemistry for doing this, but it does. Okay, Zn is being oxidized. Okay, Cu2 is being reduced. But because it is being oxidized, then it is also the thing that is causing the other compound to reduce. Okay, So it would also be called the reducing agent. If you are being oxidized, you are the reducing agent. You are what is causing the reaction. Okay? With the other one, if you are being reduced, then that means that you are the oxidizing agent. You are what is causing this to oxidize. Okay? So be prepared for being able to pick out the reducing agent and the oxidizing agent. And all of this will make sense in just a second. We'll get to it. Okay? So let's practice. And maybe I'll show you the rules first. And then we'll come back to this. Okay? I just decided that's what we're going to do. So how do we figure out how to use oxidation numbers or what their charges are? Okay, you know how to find charges. And this is going to be a little different. So don't get the two completely confused. You still need to know how to find charges for this. Okay, so when I talk about the oxidation number, I am talking about the charge on the atom or the molecule that we're talking about. And then we're going to look at the electrons that are transferred between these. So some rules. Top them all up. Okay, all the ones on this slide anyways. Okay, so for oxidation numbers, when we're giving elements oxidation numbers within our equation, the first rule is that all single elements, all elements that are completely by themselves, have an oxidation number of 0. Okay, this includes things like this. This hydrogen is completely by itself, even though there's partner. We call it a free element. So it would have an oxidation number of 0. Oxygen, 2, is going to have an oxidation number of 0. Any of these, Na, Be, any of these, and any of the elements within any equation that are by themselves are going to just automatically get an oxidation number of 0. Okay. Monoatomic ions. These are going to be elements with charges. Their oxidation number is going to match the charge. Okay, so if we're looking at Li plus, the charge on there is a +1. And so that is what we give it. We give it a +1 oxidation number. Okay, here if we were dealing with Fe, it's got a 3+ charge, so the oxidation number is going to be +3. And here, oxidation 2 minus 2 here. Okay, so monoatomic ions or single ions use the charge that's associated with them. Okay, now oxygen also gets its own special charge. It's always going to be a -2, except for in one circumstance, which is H2O2, in which case it's a -1. Okay, so oxygen is just always given an oxidation number of -2. Lots of rules, gotta love them. Okay, so number 4, oxidation numbers of hydrogen are going to be +1, except for when it's bonded to metals in binary compounds. So I will point that out, okay, if that happens. In that case, then our hydrogens are going to be a -1 oxidation. Groups 1A metals are going to always have a +1. 2A metals are a +2. Fluorine is a -1. Okay, so we go by the charges on those when in compounds. The sum of all of our oxidation numbers of all of our atoms in the molecule or within a compound must equal 0. Okay, and we'll talk about that in a second. And then the last thing is oxidation numbers. They don't have to be whole integers. Most of the time they are going to be, but there are going to be some times where you see this, and generally I won't test you on something like that. I don't think it's fair. So let me show you how we're going to do this. Okay, and I have my way. You can go and find any other way that you think is appropriate to solve these. Okay, so we're just going to start with looking for oxidation numbers within this compound. Okay, so Again, do this any way you're comfortable. I'm going to take this and I'm going to rewrite it up here. So we're going to have HCO3 negative. Okay. Based on all of these rules, I need to look at my overall equation. And I do see that my overall equation has a charge of negative. So I need to keep that in mind. That's a -1, okay, even though it doesn't say 1, gotta assume it is. And so what I'm trying to do is make this overall compound have a -1 charge. Okay. And so what I like to do is I like to go under each element and draw a circle. So in this one, I have hydrogen, carbon, and oxygen, and I drew a circle under each one, so I know I have 3 elements. And then under that, I like to draw a square. Okay. In my squares, I want you to write your charges. For your oxidation numbers. Okay. In your green boxes, I want you to tell me how many atoms you have. Okay, because that matters. So let's look at this. If we look at hydrogen, I know that I have 1 hydrogen, I have 1 carbon, and I have an oxygen 3 times. So I have 3 oxygens. Okay, now with oxidation numbers, this is where it needs to take a little bit. Okay, so right here, I need to put the oxidation number for anything that I know. And I'm always going to start with oxygens and hydrogens because we have a rule based on oxygens and hydrogens, right? What was our rule for oxygen? We go back to the last slide. Here's our rule for oxygen, right? Right here, right? Okay, so oxygen usually has a -2, unless it's with this, and that's not the compound we're dealing with. So let's go put -2 in that box. Now you should know the rules for a couple of these. If you don't know the rules for all of them, that's good. Okay, so with hydrogen, we know another rule with hydrogens, right? So if we go back to rules right here, where's my rule on hydrogen? Oh, maybe it's on my second page. Yep, there it is. The very first rule there, it says that hydrogen is going to be a +1, except for when bonded to binary compounds. Binary meaning 2. This obviously has 3, so we know it's going to be a +1. Okay, we don't know carbon. We're going to come back to carbon in just a second. Okay, at least we're not going to look it up yet. We're going to figure it out. So now what we do is basically go from top to bottom and figure out how many overall oxidations we get from each one of these. So we're going to take 3 times -2, and we end up with -6. Okay. If we add that to carbon, which we don't know yet, so leave a blank spot, and hydrogen. Hydrogen is 1 times 1, so we have a +1. Okay, so we have a +1 plus this, what we don't know, and this -6. And we want to end up with whatever our charge is. So we want to end up with a -1. So right now, if we take a -6 and add it to a +1, we end up with a -5, and that's not what we want. We want a -1. So what number could we put here to cause this to be a -1? And hopefully you all said, well, let's put a +5. If we put a +5, sorry, hopefully you all said +4. Hopefully you're not following me. If you put a +4 there, then you have +4. Add that to 1, we have 5. So we have +5. And we're going to add all of that to a -6. And we come up with, hopefully, -1. So let's try it. +5 plus a -6 gives us, yep, a -1. So that matches the overall charge right up here. And so now we know that 1 times 4 gives us our overall charge, correct charge. Okay, so then we just fill in that box. Let's check our answer. Let me erase everything I have. Oops. Sorry, trying to erase it. Okay. And so we did. We knew oxygen had a -2. We know hydrogen had a +1. And carbon, we figured, was 4. So we've done everything correctly. Okay. Again, if you don't like the circle square thing, don't use it. Use with whatever works easiest in your brain. I like it because it keeps things easy for me. Okay, then we also have a way we can check ourselves. Unfortunately, sometimes our checks don't always make it as easy as we want. But this is the chart, this is located in your book, of all the oxidation numbers of all elements. And so you can see some elements, like these over here, let me draw an arrow, have 1 oxidation number. So you cannot go wrong with that oxidation number. Some of them, though, like these, have multiple oxidation numbers. And so what you want to do is figure out the compound based on the oxidation numbers you know, or that stay the same. And then normally you'll figure it out what this is. Then just check yourself to make sure it's one of the options under that element. Okay, so let's try these. NaIO3. The next one is IF7. And then the last one is K2CR2O7. Let's give these a whirl. So with Na, I'll help you out. I'm going to write up here and then I'll erase it because I know it's NaIO3. Okay. I am going to do circles under each compound. I know I have Na, I have I, and I have O. Squares under each one of those. Okay. Then I like to draw lines. Overall charge, 0. Okay, there's nothing else listed. We're going to say it's 0. So I have 10 bubbles to fill in. Let's fill these in. I know that I have 3 oxygen, 1 iodine, and 1 Na. I know my oxidation numbers based on my rules tell me that I always have a -2 oxidation for oxygen. And for Na, it's a metal in group 1, and it tells me I always have a +1 for that one. Okay, and I don't know iodine. So let's work with that. Okay, so this I end up with a -6. This I end up with a +1. If I add all of those together right now, I'm going to end up with -5, which is not what I want. So I need to figure out what this is going to be. So it's +1 plus this, whatever it is, plus this. Okay. And if I put, again, a +4 here, +4 plus 1 gives me a +5, and we're going to add that to a negative, oops, let's do this as a 5, I'm obviously daydreaming. Okay, 5, that gives me a 6. A +6 minus a 6 gives me 0. Okay, so then we know this is 1 times 5. Okay, so these are all my oxidation numbers right here. Na would be 1, I would be 5, and Oh, it would be -2. So let's just jump back and see if this is allowable for I. Okay, so NA we did 1, we have O, there's lots of options, but we were told to use -2 unless we're one of the circumstances. Okay, and on I, my possible things for I are +7, +5, 1, and -1. We had a +5, so it is allowable, and so it's probably correct. Okay, let's double check it. We are correct. Okay. I don't know why the correct drawing isn't showing. Okay, I7. IF7. Let's try that one. We'll do circles. Under it, let's do some squares. We only have 2 this time. Okay, with 7, we had a rule for 7. Okay, we know that 7, there are, well, with F there are 7, with I there's 1. Okay, our rule with F, if we go back to our rule page, says chlorine is always a -1. Okay, so let's go, and even if you look on here, chlorine is always a -1. Okay, so we're going to write that. Pop these up again. Oops. Chlorine then has a -1. Okay, so right now we have -7 right here. We need this overall compound to be 0. Okay, so this one is going to have to be a +7. Because then +7 plus a -7 gives us 0. And that is exactly correct. Okay, and we could check that again to make sure that iodine is allowed to have that, and we saw iodine could have a +7 as well. Okay, do the last one on your own. I'm not going to help you with this. Hopefully you picked out the obvious. Hopefully you said oxygen, you know, is a -2 and you have 7 of them. Okay. Kr, also a very obvious one for oxidation. You should see that you have 2 Krs and they each have an oxidation number of -1. Okay, if we figure that compound out, we find out that we have Cr equals a +6. Okay. Good. Practice those on your own. We're going to do the same thing within the equations then. Okay, so within oxidation reduction reactions, we can take this entire equation and break it down just the way we just did. Okay, the rules tell us that if there's a charge, then that has to equal that charge, but otherwise it would be 0, like a free element would be 0. Okay, here's a charge, here's a 0. Okay, so we have to consider all that. But we can break all of these down and determine oxidation numbers for each element within this just by using this setup. Okay, so rules are free elements are always 0. So there's my free element, unless otherwise indicated. Okay, so that if we look at this Cl negative, we know it's going to be a -1. Okay. If we figure it out for this compound, again, 0, 0, square, square, square. Okay, we've got one of these. This we know is a -2. This we don't know. We need it to equal an overall -1 charge. And so here we have -2. And so here we would have to have a 1, because 1 times 1 gives me a +1, plus a -2 gives me a -1. Okay, so this is a +1. Okay, we can do the same for the other compounds if we cared about them. If we didn't, then we could just pick partners, and we could see that this Cl is partner from here to here, if we're looking at those two, or if we're looking at this Cl from here to here, we can see that from here to here, right, this one, my Cl, oops, give my phone a chance here.